Hello, everyone. My name is Christopher Mick, and I run the STEAM educational nonprofit called Space St. Croix here in Hudson, Wisconsin. And normally, every year, I'm doing on-site programs at all the area schools, the YMCA, United Way, the library, and do presentations on a variety of topics. And unfortunately, this year with COVID-19 restrictions, we've had to move to doing everything in more of a virtual setting. So this following program is on spectroscopy, one of my favorite subjects. It sounds like you might be a little bit familiar with it, so forgive me on the review here if you know some of these basic concepts, but depending on the crowd I'm talking to, they're up to speed in a little bit different areas on spectroscopy and have some questions on things. So again, my name is Christopher Mick, and I will get going on the presentation here. Oh yes, and it's Women's History Month. So I wanted to give a shout out to all the amazing women that are working at NASA currently and in the past. So you may recognize, if you can see my cursor here, some figures in the past like Katherine Johnson. Her character was featured in the movie Hidden Figures, if you'd seen that film. And then you have the first class of shuttle astronauts. First time female astronauts were brought into the ranks of NASA and included Sally Ride, who was the first American astronaut to fly into space, and Dr. Kathy Sullivan, who helped deploy the Hubble Space Telescope, which is still in service today. So I wanted to give a shout out to Women's History Month being celebrated around the country and especially at NASA this month. So just a refresher on spectroscopy. So again, if you can see my cursor here, visible light spectrum is where we are in this little rainbow area in the center. So that's what we can see register with the human eye. So on the scale at the top here, you'll see some things that technology and that you're familiar with, but we can't discern with our vision. So radio waves are these long wave patterns. Obviously, if we could see those, you'd be seeing those flying around everywhere. Any of you, your radio reception in the school or in a car, you're getting those radio waves. Same thing with cell phones are using radio waves. So they're not visible to us in the eye. We can develop devices to see radio waves. Microwaves, assuming a lot of you have access to a microwave at school or at your homes, same kind of concept where a slightly shorter wave being generated, we can have devices that can detect and visualize microwaves for us, but we can't see them with the naked eye. Infrared has gotten more common of late to general lay people in that infrared thermometers are being used a lot with the COVID-19 situation. So that's, if you've gone through that, that's when they're just scanning your forehead quickly to get the surface temperature of your forehead close to that 98.6. And so people are having more experience with infrared detectors, the handheld kind that are more omnipresent than they usually are. Visible spectrum, we talked about what we're seeing, and then you move to the other side of the ledger, and we're getting into ultraviolet light, X-ray, and gamma ray. So X-ray, again, most of you might have had some direct experience with. If they've ever let you see your X-rays, you're at a dental cleaning, anybody's had a broken bone, seen an X-ray for that. So X-rays, much higher energy wave, and that leads to it being used for seeing inside the body. Again, X-rays we can visualize in a cosmic situation, and then hopefully nobody's had any experience with gamma rays, very high energy particle, more severe form of radiation that would cause damage to us in an exposure setting. So kind of a color spectrum representation, the wave representation of those different wavelengths at the top. And then my presentations are kind of in the way NASA uses spectrometers specifically. There's many different ways to use them, but going on the history of spacecraft, Mariner 6 and 7, which were deployed, twin spacecraft, identical looking. You're getting a top view here at the top and a bottom view on the lower portion of the slide to kind of show you where the spectrometers were located on the spacecraft. But these were launched in mid-1969. And in the timeline, most of you are probably familiar with Neil Armstrong being the first person to walk on the moon, and that also happened in 1969. So a pretty big year in exploration. We were sending the first astronauts to land on the moon, and we were also sending the first spacecraft out past the Earth to explore planets nearby in our solar system, and they were armed with spectrometers, which allowed them to give us a lot of insight into the composition of those planets that we weren't able to determine without directly sending astronauts to go sample the surface. So this is a inset photo of the actual spectrometer developed, and then here's where it was located on the bottom of the spacecraft. You see the narrow angle TV for getting the still images, a wide angle, and then a radiometer, a UV spectrometer, and an infrared spectrometer. So those were able to give us our first understandings of what was making up the Martian atmosphere and items on the Martian surface. So yes, here's my bad joke for the day, a Mars bar. So if you can think of spectroscopy as the light you are reading, kind of like the ingredients on anything you're buying for a food product. So that light is containing all the ingredients are embedded in there in the light you're receiving. So if you follow my bad metaphor there, it's analyzing that light and breaking it down, and you can see in the spectrum what materials are present depending on what you're scanning. If it's the atmosphere or the rocks on the surface, all that information is embedded in the light there. So it's been used to study planets. And then this is the Hubble Space Telescope, which is looking at galaxies and other stars, is another way to use spectroscopy to gain insight information on things you can't sample directly. And this is a sister telescope to the Hubble Space Telescope. This is an image from the Chandra Observatory. And it just gives you an example of, most of you have probably seen pictures like this from the Hubble Space Telescope imaging other galaxies far away from our own, usually dozens, if not hundreds of light years away. And it'll make a composite image, which is this. And it's interesting when you see the breakdown here, because this is showing you the different wavelengths. We looked at that chart before where it's showing you what's being seen in X-ray, what's being seen in ultraviolet. Optical is what we would see with our eyes, and then infrared. All those are combined in this composite image to show us all the things that are being seen and detected, the matter and the information there. And it's being shown in some false color to give us an indication of all that's there, even though all we would be seeing if we were flying by in a spaceship and looking out the window, we would just be obviously seeing in the optical. So this is not what we would see with our eyes, but this is all the information that's there. So another bad metaphor when I'm teaching younger kids about spectroscopy is it's like a really fancy camera on the latest Android or iPhone, however many megapixels you can get, that you're just getting more and more information in the photo. You can zoom it, blow it up more, and you can notice more detail than you even would with your naked eye. And so that's not a perfect metaphor, but that's for younger kids than you, I kind of explain it to, and you get a nice breakdown here. So any telescope that has infrared to X-ray detectors, these are the different information streams they're getting, data downloads, and then they can be composited in an image that can give us more of an indication of all the detail that's actually out there. Another famous photo from the Hubble Space Telescope, and then another way of seeing that information. So this following graph is from a Earth observation satellite called Landsat, and it's scanning the light reflected back up to the satellite as it's orbiting the Earth. And so you're seeing the wavelength spectrum here at the bottom, and then how that corresponds to these spikes and what they represent. So I don't need to explain too much. You can see it all there, but the oxygen spikes, hydrogen, things like that, is how it's seen on a spectrometer. And then if you pay careful attention to the sulfur spikes here at the end and the corresponding color, that's going to tie into the next slide here. This is one of Jupiter's moons called Io, and it's got a lot of active volcanoes. It was the first planet or moon that we detected active volcanism happening anywhere other than the Earth. So it was first detected by the Voyager spacecraft pictured here. You have some engineers at the bottom for size reference on how big the Voyager 1 and Voyager 2 spacecraft are. And this is when it's kind of in its origami position, where it was being packed into the rocket. And then after it got into space and the aeroshell was jettisoned, it was able to kind of unfold and expand to its full operational position. And that's an artist depiction of Voyager 1 and Voyager 2, or twin spacecraft, what it would look like flying through space right now. So there's a whole lot of text here on the left. I'm just going to quickly go through it, but the Voyager spacecraft are both still operating. They were launched in 1977, and they are both still sending data back every day. As you can guess, it takes longer to send and receive signals with each passing day. Voyager 1 is on the order of about 20 hours one-way light time. So that means it takes 20 hours to receive the data that Voyager 1 is sending back. And if we send it commands, it's a 20-hour one-way trip to send the commands. So it's getting way out there. It's actually beyond the edge of the orbits of Pluto. And it's past what we've called the heliopause, the heliosphere, which is the kind of sun's influence on our solar system. It's past that area. So it's in what we call interstellar space now. So these are the furthest operational man-made objects that have ever been sent out into space. And again, they are both still healthy and transmitting data back. But they carried spectrometers. And it's listed here, the kind they had. They had a UVS, which is an acronym for Ultraviolet Spectrometer, and then an IRIS, which is an infrared, interferometer, spectrometer, and radiometer. There's no quiz on the terms later on. It's just giving you the breakdown of the terms. But what they do is listed here. So the IRIS can determine the distribution of heat energy a body is emitting. A body in Voyager's case was any planets that it was orbiting or moons. So it could point its IRIS and UVS at that object and get a heat energy reading on how much internal heat that planet or moon possessed. And it was emanating back out, or reflected energy from the sun. Was it absorbing more sunlight than it was reflecting, or vice versa? It could also determine certain types of elements or compounds to be found in the atmosphere or on the surface. So Voyager 1, for instance, explored Jupiter and then Saturn, and then scientists really wanted to get a closer look at Saturn's largest moon, Titan, which has a dense atmosphere and was very hard to see surface features, but it intrigued scientists on the possible presence of organics and other things that might be going on with Titan. So the orbit, or the trajectory rather, of Voyager 1 was bent around Saturn to allow it to get a closer look at Titan. That prevented it from being able to explore any other planets, but Voyager 2 was coming along behind, and Voyager 2 explored Jupiter and Saturn as well, but then it went on to explore Uranus and Neptune before ending its primary mission. So the other instruments on board could determine the total amount of sunlight being reflected in those multiple spectrums we looked at before, in ultraviolet, infrared, and visible light. So those gave us a lot of information on planets that we had no information on before in that way. And even to date, we're coming up on it, it's approaching its 50th anniversary of operation. Voyager 2 is the only spacecraft to ever visit Uranus and Neptune for those flyby missions. We have not sent any other spacecraft since, nor has any other country. So it's really precious data that we've gotten back. And this shows the trajectory of, you have artist depiction here of the Voyager 1, Voyager 2 spacecraft and the planets they explored. You see Jupiter, Saturn, Uranus, and Neptune, and some of their moons pictured there. And then the photo on the left is just kind of an overhead. If you were looking down on the solar system, the trajectories of the two spacecraft. I talked about how they kind of had similar trajectories starting out and both hitting Jupiter and Saturn, but then to get that close look at Titan, we had to eccentrically bend the trajectory of Voyager 1. So it kind of kept going out this way in the solar system. But then since that was successful, Voyager 2 was able to have a different flight plan and be able to intersect Uranus and Neptune. And these are the years that those happened, 1986 and 1989. And this was a unique opportunity because, as you can see, all the planets are kind of on the same side of the sun. And that's a very unusual alignment, only happens about every 150 years or so. And so if we launched in the 1977 time frame, we'd be able to take advantage of using what we call gravity assist, where you go by a planet and you go by at a certain speed and a certain distance that allows you to kind of slingshot around that planet, use the planet's gravity to throw you onwards to the next planet. And that would only work if you had an alignment like this of the planets, because you kind of have to be able to keep going in a progressive way. You can't double back and hang a hard left and go backwards the other direction through the solar system. So this was a unique opportunity that allowed us to explore the outer planets that had not been visited by a spacecraft before. And now getting to a current mission. So we have, this is the Perseverance rover, which has been in a lot of news coverage you may have heard about, recently landed on Mars in February 18th, just recently here this year. So this is what the Perseverance, an artist's depiction of what it looks like on the Martian surface with all the instruments fully deployed. So it has a lot of interesting hardware and software operating on it, but we're specifically talking about Sherlock and Pixel in spectroscopy. So Sherlock and Watson, yes, it's that Sherlock and Watson is a kind of dual system on an ultraviolet spectrometer with a really high resolution camera called Watson. And then Pixel is an X-ray spectrometer. So it's analyzing these particles, also has a laser to be able to gain insight into the makeup of the Martian surface at that area. And Sherlock is another acronym. So the breakdown here for Sherlock is the scanning habitable environments with Raman and luminescence for organics and chemicals. So we'll explain that in a little bit greater detail here, but I wanted to show out the darker circle you see here. This is Jezero crater, the larger area, and this black circle represents the landing target for the Perseverance rover. And it landed right about where my cursor is and almost hit dead bullseye in the center of the landing ellipse. And I wanted to show you this. This is an overhead photo, false color, from the Mars Reconnaissance orbiter. We have another spacecraft that's in orbit around Mars, and it took this photo when it was researching potential landing sites for the rover. And the reason this is important to see is because the reason the rover was sent there is what's pictured here. And that's what we call an alluvial fan. And that happens, you may have seen this in walks when you've explored parks or even in your neighborhood when there's a kind of dried up creek bed, riverbed. You have this alluvial fan. At one time, Mars had oceans and bodies of water in lakes and craters. And water, as you can see, was inlet into this crater and pushed all this sediment and material from higher up into the crater. And now it's dry. There's obviously not any flowing oceans on Mars anymore, but this is evidence of there being flowing water. And this alluvial fan is when water was pushing all that material out and into this fan-like structure because water was pushing into the crater and blowing through the wall of the crater and pushing all that material in. So we know that there was flowing water and standing water in this area at one time. And much like in Earth's ancient history, we've found evidence of fossilized microbial life on Earth in a similar situation on Earth. So the thought process was maybe similar events happened on Mars in its ancient history, and the Perseverance rover may be able to find areas where there are fossilized microorganisms in the rock, like we might find in a geology expedition here on Earth in a similar structured area. And so that's why it's been sent to explore here. So the spectrometers it has on board will allow it to kind of scan that area and determine if there's organics and possibly the right conditions for life to have once lived on Mars. So the Raman is a little bit different if you look in the acronym there. So Raman refers to a specific type of Raman spectroscopy. And it's named after an Indian physicist named C.V. Raman, who discovered the light scattering effect in the 1920s. And I like how it ties into the science we're talking about because the story goes, Dr. Raman was traveling by ship and he was trying to discover why the color of the sea was blue. A great question that a kid might ask you. Why is the sky blue? Why is the sea blue? And he had that question. And he realized that if you shine a light beam on the surface of the ocean, it can change the wavelength of scattered light depending on the materials in the surface of the water. So that's the specific type of spectroscopy he invented. and explored. And so that's why the instrument that's on the Perseverance rover is named a Raman spectroscopy. It has a laser to mimic what he was talking about in his ocean experiments, but it'll shine that laser on the material to be studied, and it'll measure the scale on how that light is scattered after the laser is aimed at those organics. So it's going to be able to classify the organics and minerals present in the rock and in the alluvial fan area it's going to explore, and it'll be able to determine if there was salty water there. There could be the formation of different minerals than in a freshwater area. And it's going to be looking for astrobiology clues, organic molecules, some biosignatures in the material that might have been evidence of past life living there. And then if it finds those areas that thinks are a prime candidate, it's going to drill those areas. This is the Perseverance rover. It has a drill head, kind of a hollowed out tube that'll allow it to drill right into the rock and capture a cross section of the rock, kind of in a sidewalk chalk size piece, which it'll then weigh and photograph and encapsulate in these sample return tubes that'll look like this. This is an artist depiction of, if it finds an area that's a prime candidate, it's going to drill it, seal it in this tube, and drop it on the surface. And in 2026, I put a question mark because that's the current hope, to launch this mission by 2026. That obviously depends on NASA funding and some other factors, but the Mars sample returns being designed right now, because the Perseverance rover has about 40 of these sample tubes on board, that it can do 40 different drill samples, cache them up, and leave them on the surface. So hopefully in 2026, a lander that looks much like this artist conception will land on the surface with 2 solar panels for power. It'll deploy this ramp, and this much smaller, it's called a fetch rover right now, because that's its only job. The Perseverance rover is about the size of a car, weighs just over 2,000 pounds. The fetch rover will be much smaller, just designed to pick up these sample return tubes. So it will land near where Perseverance landed, deploy the rover will drive around and pick up hopefully close to 40 of these sample tubes if they're all used. It will drive back to the landing site, drive up this ramp. There's an arm that will collect the sample tubes and put them in the storage area, payload area of this rocket. This is all going to happen automated, obviously. And then the rocket will launch from the surface of Mars. First time we've ever launched a rocket off of the surface of Mars. We'll go into orbit and be intercepted by another spacecraft that's being built by the European Space Agency. They're partnering with NASA on this. That'll be met in orbit. We'll catch that sample of tubes, and then that spacecraft will return to the Earth and deploy a lander, a reentry vehicle that will have a heat shield to protect it from the Earth's atmosphere. It'll have parachutes that will deploy, and it will land and be recovered. And that'll be the first time we'll have Mars samples returned to Earth for further analysis. So there's a lot of science on board the rover, but some of the amazing labs that are room-size labs we have on Earth, it's just not possible to miniaturize those down to get those on the rover. So when it finds potential great candidates for further study, it's going to wrap those up and hopefully be returning those to the Earth for further study. And we may get the first confirmed evidence then of microbial life having lived off of the Earth on Mars. And so that's one of the amazing things about spectroscopy. It allows us to gain insight into things that we can't directly go sample and study. So be it stars or galaxies, exoplanets further away from the Earth, hundreds of light years we're able to study, and then all the planets and moons in our solar system. And then it allows us to kind of zero in on candidates where we might want to send astronauts in the future if we can do that, or like this intermediate step of being able to bring samples back for further study on the Earth and do that. So that's kind of an insight into how NASA looks at spectroscopy and some of the future missions that might be coming up, and a little bit of history for it. So it's a really interesting field. if I was there in person, I've got these great little cards that kind of show you can hold them up to different lights like quartz halogen and incandescent bulbs and LED lights. And it has a little filter in there, and it allows you to see how spectroscopy works on these automated machines, because you'll notice a different arrangement of the kind of spectrum of light there, that kind of rainbow gradient. You'll see the blues and the greens and the reds, but they're arranged differently, and there's little line breaks in them depending on what type of light you're looking at. And that's like a great on-hand, real-time way to see how spectroscopy works. And unfortunately, again, I can't be there to hand out those cards or to bring in some of those fun lights for you to see how this process works in person. But hopefully you can kind of understand a little bit about how that process works, and have an appreciation for how scientists use those tools to find out what rocks are made of that they can't go pick up, or what might be happening chemically in the atmosphere that they can't directly sample, and things like that. So it's a very interesting field of science, and I'm really happy to be able to talk to you about it a little bit today. And thanks for listening. Hopefully we'll be able to see you in person next time. Thank you very much.